Okay, so we've looked at some molar mass and things, and we've used stoichiometry to convert, and that's all we've been doing right now. That is pretty much the dimensional analysis, but the actual true stoichiometry applies to equations and things we would actually use in chemistry that we can use in a real-life lab setting. So notice this a chemical equation is not balanced. This is a combustion because it's oxygen and you get carbon dioxide and water at the end, but we're going to need to balance it. And I'm going to balance it real quick for you because I already know this one. I need 2 there. That would end up giving me 4 over here, a 6 here, and that means that I need 14 oxygen, so I need a 7 right there. Now, these are those coefficients, right? And the coefficient is multiplied by the to the entirety of the molecule. And that's important because what those really are moles of those molecules. So what this really means is for every 2 moles of ethane, which is what this is, I'm going to produce 4 moles of carbon dioxide. We call that a mole-to-mole ratio. And so I can even write this as that ethane, and then this tends to mean ratio to carbon dioxide, and I can say it's a 2-to-4 ratio. Now that's really helpful because that's 2 moles to mole of ethane to moles of carbon dioxide. And you can use that in a conversion. So let's say I had 12 moles of ethane. And I wanted to know if I put it in this chemical equation, if I combusted this basically, and that's a 2 by the way, how many moles of carbon dioxide I would get. Well, essentially what I would do is I would use my railroad tracks and I would say I know for every 2 moles of ethane, I'm going to get 4 moles of CO2. And look what happens with those units. We have moles of ethane down here. That's canceled out by moles of ethane there. But then I'm left with moles of CO2. So now if I do the math, I do 12 times 4 divided by 2, I'm going to get the moles of carbon dioxide that I would have, which is just going to be 24 moles of carbon dioxide. So I get more carbon dioxide, than moles of carbon dioxide, than moles of ethane that I put into it. Now, you might think, okay, well, I guess that's helpful for moles, but you also have to think that we do this a lot of times for how much we need to actually put in something for like grams of something. So you might get a question like this. How many grams of H2O or water do you get from 6 moles of ethane in the above equation? Well, to do that, I need 2 things. First, I need the mole-to-mole ratio of water to ethane. And so first thing I'm going to look at is for water to ethane, I have a 6-to-2 mole ratio. Okay? The next thing I need to know is I need to know the molar mass of water because that's going to be how I find out how to convert it into grams. So if you remember molar mass, you just go to the periodic table and you look up what it is for each element. And so for hydrogen, its molar mass is 1.008 grams per mole. And we have 2 of those, so we're going to use a 2 multiplier. Plus, and that's our hydrogen. And then oxygen is 16.0 grams per mole. And we only have one of those, so we don't have to worry about doing much there. That's our oxygen. And so when we multiply the hydrogen by 2 and then add it to our water, we're going to get 18.016 grams per mole. Now, with all of that, we can start with what we're given down here and work on those railroad tracks. So I'm going to start with 6 moles of ethane. Now, I need to go from moles of ethane to something else. So I'm going to need that on bottom. I'm going to need moles of ethane. And if I look, I can use that ratio. So I know that I go from 2 ethane to 6 of the water. So I'm then going to go and say that this is 2 moles of that to 6 moles of H2O. And I know that that works, right? And then I'm going to go from moles of water, 6 moles of, oh, I'm sorry, not 6. Moles of water, and I know that I go from every 1 mole of water is equal to 18.016 grams of water. And now I've just made my railroad tracks. And if you look, the units should cancel out. Moles of ethane, moles of ethane. Moles of water, moles of water. So I'm left with grams of water as my unit, and I can just multiply everything that's on top and divide by everything that's on bottom. I don't actually have to divide by 1 because anything multiplied or divided by 1 is itself. So essentially I'm going to go 6 times 6 divided by 2 times 18.016. And what I get is that it equals 324.2, I'm going to round to 9 grams of water. So whenever I go through 6 moles of ethane in a combustion, I'm going to get 324.29 grams of water out of it. And that's why this is so important. Now, you might have noticed some things like oxygen and carbon dioxide are gases. And with gases, you're not going to want to measure them in grams because you wouldn't do that in a lab setting. You would measure them in liters. And so we're going to need one other conversion. If you've looked at the reference sheet at all, you would notice that it states that at standard TP, that's just, or STP, that's just standard temperature and pressure is all that stands for. 1 mole of anything is equal to 22.4 liters of that substance. Okay, so that's another equivalency we can use. And then we already learned that our molar mass of water is 18.016 grams per mole. And now we can start to think about this equation, or this question. How many liters of O2, the gas, is needed to produce 150 grams, a liquid, of water? So in order to do something like this, I'm going to need to know that mole to liter ratio so I can change oxygen into moles, because I have no way to relate liters to grams. I can do mole to mole for oxygen to water, though, because of this equation. In fact, I need to know that ratio as well, so let's also put that under my useful materials here. And that is a, let's see, it's going to be a 7 to 6, and that's for moles of water from oxygen, right? So we're going to need all of that just in order to convert this. And then we're going to start with what we had again. They gave us 150 grams of H2O. I need to know that I have 18.016 grams of H2O in every 1 mole of H2O. And then I need to understand my mole-to-mole ratio for water is going to be 6 moles of H2O to every 7 moles of oxygen. Now I need to bring in that moles to liters though. So I know that for 1 mole of O2, I'm going to produce 22.4 liters of O2. And if you look, it'll all cancel out once again. So I have grams of water to grams of water. I then have moles of water, moles of water. I then go from moles of oxygen, moles of oxygen. And I'm left with liters of oxygen, which is what it's asking for in the equation, or in the question, right? So now it's just a matter of going through and multiplying everything on top again, dividing by everything on the bottom, and we will get 217.58 liters of O2 as our answer. So you see, this is really helpful for converting things back and forth and for even being able to go in and actually look in a lab to make certain elements or certain compounds and things using a reaction that we know will take place. And so this is a good way in order to go about to make sure you get what you need out of it. And this is why they call it stoichiometry, because it's used so much in these mole-to-mole ratios in equations. I hope that helps.